This lesson is looking at forces on an inclined plane and starting to delve into our topic of dynamics. So the inquiry question we're trying to answer is how are forces produced between objects and what effects do forces produce? And our learning intention for this particular lesson is that we will understand how forces behave on an inclined plane. So to start off with, I want you to draw this diagram in your book and label all of the forces present using your knowledge of Newton's laws and forces. Okay, so just pause the video here and do that. Alright, so an object on a tilted surface will often slide down the surface if the forces overcome the force of friction. The rate at which it slides down is dependent on how tilted the surface is. If it's more tilted, then it's going to slide down faster. Okay, so you should know that just from your observations of real life. In physics, a tilted surface is called an inclined plane. Objects are known to accelerate down inclined planes because of the unbalanced force. To understand this type of motion, it's important to analyse all of the different forces that are involved and are acting on the object that's on the plane. The normal force is not necessarily directly upwards, but it is perpendicular to the surface the object is on. So in this case, we're looking at an inclined plane, and that means that the normal force is going to be perpendicular, so that means at right angles to the surface it's on. Okay, so this plane here, the incline, that's the surface, and the normal is at 90 degrees. Here are some other examples of different planes so that you can see that the normal's at 90 degrees to the surface. Okay, so another really important thing. So mass is the amount of matter that you're made up of, and this doesn't change. So this is important when we're looking at the force of gravity on the object on the inclined plane. Mass and weight are very different. Weight is actually dependent on the gravitational force that the Earth exerts on you. Okay, so your mass, doesn't matter where you are. You could be on the moon, you could be on Earth, you could be on another planet. Your mass, it's the amount of matter that you're made up of, so it does not change, it will remain the same. But your weight will change because the moon has a different force of gravity to Earth, and so your weight will change. So because we know that the force of gravity, the pull of gravity is 9.8 newtons per kilogram, on Earth your weight would be your mass in kilograms multiplied by that force, so 9.8 newtons per kilogram. And this is just a cool cartoon that I found that I thought you would enjoy. Alright, so I want you to pause the video here again, and I want you to determine what your weight would be on other planets. So just have a guess at what your mass is right now, so the last time you weighed yourself, roughly what you think it is, and then work out what your weight would be on these different planets. Okay, so here we're looking at the weight or the force of gravity acting on the mass of the object in this force diagram here. So the weight of the object is equivalent to the mass of the object multiplied by the force of gravity. So exactly the same as what you just worked out for your own mass and weight works here in this diagram as well. And obviously the pull of gravity is directly downwards, okay, down towards the center of the Earth. So the force of gravity is often written like this, or you might see it as the force of the weight is the mass of the object multiplied by the force of gravity, which, unless you're told otherwise, you assume is 9.8 newtons per kilogram. Alright, here are three different scenarios, so I'd like you to again pause the video here, and I want you to determine what the force of gravity is, or the weight of each of these objects would be on the inclined plane. Once we've worked out our force of gravity, we can then work out the components that it's made up of. So just like in our kinematics topic, we can find out the x and y components of that force. So the diagram here shows you where those components are. So you've got a component that is parallel. So this those two little lines are talking about it being parallel to the inclined plane. Where this one is talking about it being perpendicular to the inclined plane, and you'll notice that that is in the same direction as the normal. Okay, so the normal would be coming up this way, and here the component, the y component of the force of gravity is perpendicular to the inclined plane. Okay, so this here is your x component, and this here is your y component. So the perpendicular or y component of the force of gravity is directed opposite of to the normal force, as I just said, and the parallel component is often balanced by the force of friction. So here you can see the normal force, and here's the force of friction, and this would be your x component or your parallel component of your force of gravity. If there's little or no friction, then the object will slide and it will accelerate down the inclined plane due to the presence of that unbalanced force. If the forces are balanced, then you know it will stay stationary, okay? And if the force this way, like if we had someone pulling it up the ramp, then obviously it would be moving up the ramp. Okay, now to determine the magnitude of each of these components, we need to use our sine and cos, or our trigonometry rules, which we also use in our kinematics topic. So the equations for the parallel and perpendicular components, one thing to note is that the angle here that's made with the inclined plane, that angle is exactly the same angle as the angle that's made between the force of gravity and the perpendicular or the y component of that force. So this angle here is the same as this angle here, and often, well, almost always you'll be given this angle here of the inclined plane, so you can start with an angle here. Once you've worked out your force of gravity, then it's just working out what rule you'd like to use. So if this is your right angle triangle and your right angle was in here, okay, you've got your angle, you know the hypotenuse, and you're trying to find the adjacent side. So to work out your y component, you'll be using cos, okay, so cos of theta equals adjacent over hypotenuse, right? And then in the same way, if you're working out your x component, then you're looking for the opposite side of the triangle, and so you can sort of bring that arrow down here for your x component, and it would be opposite over hypotenuse. Okay, and so that would give you, if you rearrange them, these two equations. So if you hadn't already worked out what the force of gravity was, then it would be the mass times gravity, so mass times 9.8, then sine of theta, that's for your parallel or your x component, that's this one here, or this one here. Okay, for this one you would have mass times gravity, okay, times cos of theta. Okay, and that would give you your y component here. This diagram is just showing you those equations to work out the magnitude of those vectors there. What I'd like you to do here is have a go at finding the x component of f1 and also the y component of f1. Okay, so that means the x component is looking here and using this equation here that we've just worked out, and the y component would be using this one. Okay, so pause the video here, use this scenario to determine both A and B. All right, working through the answer to A. So to find the x component, we've got the mass times gravity, sine of theta. Now the mass of the object is told to be 10 kilograms, okay, and it's important that we keep our measurement in kilograms. So if you were given it in grams, you should convert it to kilograms, because your force of gravity is in newtons per kilogram. So you need to make sure your units are the same that you're working with. So 10 kilograms times force of gravity, 9.8, times sine of the angle, and we're told that the angle of the ramp is 25 degrees. So your answer should be 41 newtons, and that's correct to two significant figures. For the y component, okay, the mass is the same, so still 10, gravity is the same, 9.8, but this time you're using cos of the angle, so cos of 25 degrees, and you'll end up with 89 newtons, correct to two significant figures. What I'd like you to do is pause the video here if you think you're ready, and have a go at working out the x and y components for each of the examples here. If you don't feel like you're ready, that's okay. Keep watching the video, don't pause it just yet, and I'll step through step by step for each of these examples for you. Okay, so if we're trying to find the x and y components of F1, or force of gravity, so that you understand where these formulas are coming from, if we draw in a right angle triangle here, okay, this angle in here is the same as this one, so this here is going to be 20 degrees as well. Okay, and when we're trying to find the x component, so let's start with the x component, that's going to be this one here. Okay, so if we're trying to find the x component first, it's going to be sine, because we've got opposite, and the hypotenuse. Now we can work out the hypotenuse because that is the mass times the force of gravity. And so our formula is mass times gravity times sine of theta. So in this case, the mass is 15 kilograms. Times the force of gravity, 9.8 meters per kilogram, times sine of 20 degrees. So if we put all of that in the calculator, the answer is 50 newtons. Now we're trying to work out the y component, that's this one here. Okay, and this one we're using cos because we've got the adjacent side and the hypotenuse. So I might just draw this over here. So y equals, so mass, again, times gravity, times cos of the angle. In this case, the mass is 15, times gravity, times cos of 20. 138 meters. Okay, so here we've found the x component and the y component for our first example. So let's try the second example. So same formula for these. So for the x component, the mass of this example is 50 kilograms. And the angle in this case is 30 degrees. For the y, same formula as before. So the mass times gravity, but this time cos of theta. The mass is 50 kilograms. Gravity is 9.8. And the angle is 30 degrees. Okay, so I'll leave the third example in the presentation for you to have a go at of yourself. But sometimes it does help you to actually draw your right angle triangle and work out where the x and y component is, just to make sure that you're not getting your sine and cos mixed up. Good luck.